Industrial environments are like finely tuned orchestras, with various electronic components working in harmony to achieve complex tasks. At the heart of this orchestra lies the Programmable Logic Controller, or PLC, which is really the conductor that dictates every movement. It receives signals from sensors, much like a conductor interprets musical notes, and based on pre-programmed logic, commands actuators into action. Imagine a conveyor belt system in a factory. Sensors along the belt detect the presence of objects, relaying this information to the PLC. The PLC, following its programmed instructions, then directs actuators to move the belt, stop it, or adjust its speed as needed. This seamless interplay between sensors, PLCs, and actuators forms the backbone of most industrial automation. However, the PLC is not a solo performer. It often partners with variable frequency drives to control motor speeds efficiently, human-machine interfaces to provide visual feedback and control to operators, and supervisory control and data acquisition systems for higher-level monitoring and data logging. Together, these components form a powerful team, ensuring smooth and efficient operation of industrial processes. Think of a large-scale bottling plant. The PLC manages the overall logic of the bottling line, while variable frequency drives precisely control the speed of conveyor belts and filling machines. Operators interact with the system through HMIs, monitoring production rates and adjusting parameters as needed. Meanwhile, the SCADA system gathers data from the entire plant, providing valuable insights for optimization and predictive maintenance. Just as a musical score guides musicians, wiring diagrams and electrical schematics serve as blueprints for industrial electricians and technicians. These diagrams use standardized symbols to represent various components, their interconnections, and the flow of electrical signals. Understanding these symbols is crucial for installation, troubleshooting, and maintenance of industrial systems. For instance, a simple circuit diagram might depict a power source, a switch, and a motor connected in series. The symbols for each component, a circle with a plus and minus sign for the power source, an open and closed line segment for the switch, and a circle with the letter M for the motor, are connected by lines representing wires. More complex schematics like those for PLCs use ladder logic diagrams. These diagrams resemble a ladder, with two vertical rails representing the power supply and horizontal rungs representing individual circuits. Each rung contains symbols for inputs, outputs, and logic functions, illustrating the program's flow. Consider a PLC controlling a pump. The ladder logic diagram might show a pressure sensor as an input, a timer as a logic function, and the pump as an output. The logic dictates that if the pressure drops below a certain threshold, the timer starts. Once the timer times out, the pump is activated until the pressure returns to normal. Programming a PLC is akin to teaching the orchestra conductor a new musical piece. We use specialized software and programming languages like ladder logic or structured text to define the logic that governs the system's behavior. This involves configuring inputs, outputs, and the logical relationships between them. Let's take the example of programming a PLC to control a conveyor belt with sensors and actuators. Firstly, we need to define our inputs. Sensors detecting the presence of objects on the belt. Next, we configure outputs, actuators controlling the belt's movement. Finally, we establish the logic. If a sensor detects an object, start the belt. If no object is detected, stop the belt. Step 1. Define inputs. Assign input addresses to the sensors. For example, input 1 for sensor 1, input 2 for sensor 2, and so on. Step 2. Define outputs. Assign output addresses to the actuators. For instance, output 1 for the belt motor. Step 3. Program the logic in ladder logic. This might involve using contacts representing the sensor inputs and a coil representing the motor output. When the sensor contact closes, meaning an object is detected, the coil energizes and the motor starts. This simple program demonstrates the basic principles of PLC programming. By combining inputs, outputs, and logic functions, we can create sophisticated control systems for a wide range of industrial applications. Even the most well-tuned orchestras encounter occasional disharmony. Similarly, industrial electronic systems can experience faults, leading to downtime and production losses. Effective troubleshooting involves systematic identification and resolution of these faults. Common faults include sensor failures, communication errors between components, and actuator malfunctions. When a fault occurs, the first step is to gather information. Check for error codes on HMIs or PLCs, inspect sensors and actuators for physical damage, and verify communication links. Step 1. Identify the symptom. What is the specific problem? Is the conveyor belt not starting or is it running at the wrong speed? Step 2. Isolate the cause. Is the issue with the sensor, the PLC program, or the actuator itself? Use a multimeter to check for voltage at various points in the circuit. Step 3. Test and replace components. If a sensor is faulty, replace it. If the PLC program is incorrect, modify it. By approaching troubleshooting systematically and utilizing diagnostic tools, we can swiftly restore harmony to our industrial orchestra, minimizing downtime and ensuring smooth operation.